Back to the second video for section 5.2, the definite integral. You had worked on a couple of things now with this section where we're talking about a little bit of new vocabulary, and you had also worked on some sigma summation notations, and I just want to remind you of those. On page 329 you have a couple of rules that you can add to your toolkit, but we had looked at those three summations and some other summation rules, and we're going to apply those today when we work on begin with example 2. So here we want to evaluate the Riemann sum f of x cubed minus 6x by taking sample points to be right-hand endpoints with a is equal to 0, b is equal to 3, and n is equal to 6. So if you recall that we have, when we mentioned a, b, and c, that a is the beginning of the interval. A is the beginning of the interval at 0. B is the end of the interval. So you recall that delta x is still equal to b minus a over n, the number of subintervals that you would want. So in this, we've got our delta. You see that I've already got the delta x here, and we're looking at delta x on each section. And as you go across the interval or the partition from 0 to 3, we have our setup, and we are looking at the R6 now, Riemann sums, and we are using right-hand endpoints. So we'll be starting with the function value after the first subinterval. So we have the Riemann 6 is equal to the summation from I is equal to 1 to 6 of your f of x, your function values, sub I, times delta x sub I. And delta x sub I, delta x is all the same for each subinterval. So when we do that, I'm going to bring this down here, equal, and put a little star and bring that over here. So we have that is then equal to f of 0.5 time, and I'm just going to add the function values. I'll add the function values, and then at the end we'll multiply by delta x. So parenthesis f of 0.5 plus f of 1 plus f of 1.5 plus f of 2 plus f of 2.5 plus f of 3, big parenthesis, and then we're going to multiply by 1/2 or 0.5. So once we get that, then we're going to put the function values, so they would be negative 2.875 plus f of 1 is negative 5 plus f of 1.5 is negative 5.625 plus f of 2 is negative 4 plus f of 2.5 is 0.625 plus f of 3 is 9. Big parenthesis and multiplying by 0.5. Calculating our answer, it looks like we get negative 3.9375. Almost 4, it looks like. So when we take a look at this, it does appear that we have more area underneath. If you look at it, more area underneath the x-axis than we have above the x-axis, where we only have these two little pieces. One not so little. Okay, all right, that is an approximate Riemann sum to get the approximate area. So, and we took sample points to be right-hand endpoints. Now what we want to do in the second part B is we want to evaluate the definite integral by using Riemann sums. So, and I would kind of want to consider the approximation in the end. We are going to find r sub n with n subintervals first. So we're going to start out, we're going to say, well, delta x is equal to, we have our a and we have our b. Okay, delta x is equal to 3 minus 0 over n. So delta x is 3 over n. And then we need an x sub I. And x sub I, when we calculate it, what we're going to do is we're going to lay out, I'm going to put this down. So if I have an x sub 0, here's my x sub 1, here's my x sub 2, here's my x sub 3, and so on. All of these are separated by delta x. So most of you would say, okay, well, x sub I, if x sub 1 is equal to, it looks like where I start, because that's going to be a, it's going to be a plus I, or the number I, because it's going to be 1 times, so let's put a number in instead, 1 times delta x. Then x sub 2 will be a plus 2 times delta x. And we could continue to do this, but a mathematical mind will generally see the pattern, and you see the pattern already, where the I is this constant multiplier of delta x. So I'm going to do a little bit of erasing in a moment, but it'll be a plus I times delta x for our x sub I expression. Okay, if you have that down in your notes, you know you're following along as we go, put that in your notes and see if that makes some sense to you. And I'm going to erase this. But then I know I have some information about delta x and a. So I have x sub I then is equal to, I start at 0, plus I have I times delta x, which is now 3 over n. So I end up with an x sub I that is equal to just 3I over n. Box that up. So I'm going to need to use these two expressions in my summation. Scroll up just a tiny bit so I can still see that. So we want to find this expression for r sub n. So r sub n. So the Riemann sum with n. I'm going to go ahead and include the expressions for this. So we have an integral from 0 to 3 of x cubed minus 6x dx is then equal to the summation, or the limit, as n approaches, the number of subintervals approaches infinity, of the summation from I is equal to 1 to n of f of x sub I delta x. So now what we want to do is plug in our expressions for x sub I and delta x. So we'll forego the integral representation right now, and we'll say r sub n is then equal to the limit as n approaches infinity of the summation from I is equal to 1 to n of f of, now we need the expression for our x sub I, which is 3I over n, times delta x, which is 3 over n. Okay, so remember we're finding the Riemann sum. It is equal to the definite integral. So now what we're going to do is we are looking at the function. Now recall, let's say what the function is up here. Remember f of x, well here it is up here. The function is x cubed minus 6x. So what I need to do then is plug it in here for the function. So now I have r sub n is equal to the limit as n approaches infinity of the summation from I is equal to 1 to n of, now I'm going to use some parentheses here, so it will be 3I over n cubed minus 6 times x sub I, so it'll be, remember it's the function of 3I over n, so it'll be 3I over n times the 3 over n for the delta x on the outside. Okay. Just going to draw a little line there, scroll down a little bit. Okay, so now you see that we're going to have to simplify our expressions. So what I'm going to do is probably end up distributing the 3 over n to both terms within the summation. So let's do that first. The limit as n approaches infinity of the summation from I is equal to 1 to n. Now I'm going to take this big old thing and I'm going to say, all right, this is going to be 27i cubed over n cubed. And then it's going to be times 3 over n minus, I've got this 18i over n times 3 over n. Sometimes it's good when you're producing videos to try to be as explicit as you can. You may want to speed it up a little if you understand this. But so here we go. We have r sub n is then equal to the limit as n approaches infinity of the summation from I is equal to 1 to n of 81i cubed, 27 times 3, I cubed, over n to the 4th, minus 18 times 3 is 30 plus 24, 54, I, over n squared. And that looks like it. Oh, yep, I think that's it. Okay, pause, take a look at that. And I'm going to copy and put it on my next page, just to give me a little bit of extra room to work with. Oops. Woo. Or not. Maybe I'll just take a picture. Okay, give me a second to catch up. And take this right to the next. Okay, so now we're looking at r sub n is equal to, I'm going to take the summation and I'm going to split it apart as n approaches infinity. I have then the summation. I'm going to take the summation of the difference and make it the difference of the summation from I is equal to 1 to n of 81i cubed over n to the 4th minus the summation from I is equal to 1 to n of 54i over n squared. And I'm still taking the limit, but what I'm going to do is I'm going to pass the constants out in front of the summations. So the limit as n approaches infinity of, still in this big grouping, 81 over n to the 4th times the summation from the summation from I is equal to 1 to n of I cubed minus 54 over n, pull that constant out front, times the summation from I is equal to 1 to n of I. Okay? So now with your summations all dealt with, where you have the summation of I, you know, is equal to n times n plus 1 over 2, and you know that the summation of I squared is equal to n times n plus 1 over 2, and that would be squared. Oh, I'm sorry, I cubed. So we now have r sub n is equal to the limit as n approaches infinity. So I'm going to now substitute the expressions in for I cubed and I. So I have then 81 over n to the 4th times the quantity n times n plus 1 over 2 squared minus, then we have 54 over n times the quantity n times n plus 1 over 2. Oh, here, I'm going to bring an n squared, have a typo here. Okay, that'll fix that. All right. And scrolling down, just taking a look at things. Okay, and then putting the parenthesis in. So now we need our expressions simplified. So we get the limit as n approaches infinity of, we're going to have 81 over n to the 4th here. And if I simplify, I'm going to get n squared times n squared plus 2n plus 1 over 4 minus 54 over n squared times n squared plus n over 2. I could have simplified in the last step, but no need to. So now, as I'm looking at this, I'm almost where I want to be. I'm going to take one more step to say the limit as n approaches infinity. This is kind of beautiful that things work out like this. Let's see what we have now. So we have n to the 4th plus 2n cubed plus n squared over 4 minus 54 over n squared. And this top is very similar. I'm going to just be use a parallel step at this moment over 2. Now, I can see that with these denominators, I'm going to do a little switching here. I'm going to switch the order of these two in this step. So what I'm going to do is I'm going to write this as 4n to the 4th. So I'm going to put the 4 here and the end of the 4th, just switching the order, because I know I'm dealing with limits at infinity, and I recall that the limits at infinity, so I'm going to switch this n squared and put the 2 out front. I recall that with limits at infinity, when the degrees of the numerator and the denominator are the same, that in there, then the limit at infinity is the coefficient of the leading terms of that rational expression that you see. So let's take a close look at the rational expressions that we have in both places. And in taking our limit, we have the limit, r sub n, is equal to the limit as n approaches infinity of 81 over 4 times this whole thing. Now I'm going to take an extra step, n cubed plus n squared, just to show you the limit notation over n to the 4th, minus the limit as n approaches infinity, then, of 54 over 2. That's silly because it's 27, but we'll get it on the next round. N squared plus n over n squared. So if I take the limit of these expressions, r sub n is equal to 81 over 4 times this limit. The limit of that is going to be just 1, because we look at the coefficients of our leading terms, and we've done enough work to know that it's the leading terms that are going to pretty much boss this expression. So if I look at those, then I can come over here and I can say, oh, the same thing is going to happen over here. And if I take the pen and remember to make my fraction line in there, that might be better. So we have 81 over 4 times 1 minus the limit of the second is going to be 27, 54 divided by 2, or 27 times, and that limit will also be 1. So our final answer then would be 81 over 4, 81 over 4, minus 27 times 4 would be 80 plus 28. 80 plus 28 is 108 over 4. So we get, for an answer, we get, what do we get? Negative 6 3/4. Negative 6. Oh, negative 6. Oopsie. And 3/4. So negative 6 3/4 is our exact area to answer, exact area to answer the question for the definite integral for part B. What is the definite integral? This is exact. I feel like my pen is really not in sync. So this would be the integral from 0 to 3 of x cubed minus 6x dx. Now, comparing that to the previous answer is always interesting for me, that I would see on the previous answer we got that the approximation to the